me just talking about animals that start with M. Let's how do I mute everyone?
Mandrills, sorry.
Mandrills. I'll have to look those up. Wait. Oh, before I was there anything that I meant to do? Oh, I posted all the assignments for the rest of the term. No more, I promise. So, and there's some bonus assignments. Let's see here. Hidden from students. I should hide that in my screenshot, I guess. Secret. It's just got the outline of the final exam. But like I said, I want to make some changes to it, so I'm not ready to commit. Okay. These are the last remaining assignments. I made you work hard. But had me worried. Quite all right. And then you're sort of free. I think, when did I make them due? 18th, make you do them so that you can use them to study later maybe, or just have them out of your hair. I think it's kind of enough time anyways. And because these are your last ones, you can use up any remaining late passes and if you need more time. Okay. Assignment 19, simple linear regression is what we started last day and potentially wrapping up today. And then an Excel assignment on regression. And then I posted 2 bonus assignments, a bonus Excel assignment on multiple linear regression where we can have more than one explanatory variable, right? More than one X. And this one, I just made this one. It's on statistical process control. And yes, you guys are my guinea pigs. That's why it's a bonus assignment. And so it's another video assignment where you watch a little clip and then you do it, and then you watch a little bit more of the clip, and then you do it, and then you're done. Okay? So I've set it to drop your lowest, I guess, 4 assignments, or if I haven't, I'll make sure that I have later for all those bonus assignments. So if you do those, it'll replace a lower grade. Or if you already have 100%, then you can just let these drop. It's okay, but might be fun to try. So statistical process control is common in industry, especially manufacturing, where we want to make sure that things are kind of in control, right? And so the number of defects isn't, out of control, that kind of thing. And it has to do with standard deviations from the mean, which all sounds very familiar. Okay, so, hey, it got rid of my mouth. More of a smirk. All right, so for review, we introduced regression. Regression is the line of best fit. And like, wow. So someone on this side of the room, that's crazy.
Welcome.
Finish strong. We talked about these 2 sections of our formula sheet. Oops, let me copy properly here. Copy. Which was the end of the formula sheet, which is kind of crazy. And, well, to me at least. And what we said was, okay, the covariance, if I give you the covariance, I'm giving you this SXY. Yeah? And why would you need it? Well, there are a couple of different ways that I would give you the correlation, which is your lowercase r. And so your correlation is this guy here. Why do you need the correlation? Well, if I ask you to build a least squares regression line, which I will, I promise, okay, then you'll need the intercept and the slope of this line of best fit. And we introduced y hat. Y hat is the predicted value of y. Anything with a hat on it in a regression context is a predicted value. And our ultimate goal is to predict values of y using this line of best fit. And so then I tell you that, okay, well, the slope with a slope of b1. Right? So I tell you that the thing attached to the x is the slope. And that's the first thing that you're going to calculate, even though it's called b1 and b0. We have to find the slope first because we need it in order to find the y-intercept. And so to calculate the slope, we need the correlation, right? And remember, the correlation, R is the correlation, and it's a numerical measure of the strength and the direction of a linear relationship. R is the correlation, which is a numerical measure of the strength, right, between -1 and 1, right? 1 being a perfectly linear relationship and 0 meaning there's no relationship at all, just a cloud. And so a numerical measure of the strength and direction of a linear relationship. So we need the correlation in order to find the slope. And then we also need what? We also need the standard deviation of the y's and the standard deviation of the x's, which would be given in the problem. Once you have your slope, you're going to use it to find your y-intercept. The y-intercept, we find it by using the fact that all lines of best fit are going to pass through x bar, y bar. That's kind of a fun fact. And so, or you just use the formula, but you're going to use the slope that you found, multiply it by the mean of the x's, and then subtract that from the mean of the y's. And so for a regression question, or I should say, I will need to give you the following information. I need to give you x bar. I need to give you the standard deviation of the x's. I need to give you y bar, the mean of the y's. And I need to give you the standard deviation of the y's. Right? In terms of our spreadsheet, we're going to have a column for our x's and a column for our y's, and we can calculate the means and the standard deviations of both those things. And so I would just give you those and the correlation. Now the correlation kind of comes with an asterisk because there are a couple of different ways I could give you the correlation. And so let's see here. I'll add a page. There are, I'm going to say 3 ways I could give you the correlation. Number 1, I could just give it to you explicitly. I could tell you the correlation is this, right? And then you just have it. right? And so stated explicitly, the correlation is blank. That'd be nice. It's another option. We could say, okay, here, the correlation, well, I mean, in theory, I could make you calculate it, but man, that's mean. And I'm not gonna do that. Okay? But I might give you the covariance, right? The covariance is this SXY. Okay? And here's the formula for how you find SXY, but I'll be nice and you don't need to worry about that, and you don't need to worry about that. Yeah. They're on there for completeness, and some instructors do like to use those, but I do not. Yeah. So the meanest I could be, probably, trying to think if the third one is mean or not. No, not really. Is if I give you the covariance, right? I tell you the covariance is this. From before we said, okay, yeah, I would need to give you SX and SY anyways, right? So you'd already have those. And so then you would need to calculate the correlation, right? So then you could be given the covariance which is your SXY. Right? The covariance is blank. But then I would follow it up with calculate the correlation, or what is the correlation? Or let's say find the correlation. The third one, I am going to introduce it here, and we won't see it for a little bit today, but it is the third option. So for completeness, I'll introduce it here. And so then I might give you, given the R squared, more to come later today. So those are the three ways that I could give you the correlation. Besides that, you need these 5 pieces. And what are some questions? There's a lot of parts to a regression question, right? And so some possible questions that we've already introduced and are able to answer, right? And so questions might be something like this, or I should say possible questions. I might ask you to describe the relationship. Right? If I give you a scatter plot, describe the relationship. Describe the relationship. You have to touch on 3 things. Right? You have to talk about the strength and the direction and whether it's linear or nonlinear. I'll say linear versus nonlinear. The strength, right? Is it strong or weak? Or you can throw in some modifiers if you want, moderately strong, moderately weak, and oops, the strength and the direction. It's a nice place to start. I'll give you a scatter plot and you have to describe the relationship. Next, I might say, calculate the slope. Right? The slope from your formula sheet is r times sy over sx. Let me just confirm. You don't want to mix those up. Oh, and sometimes if I'm nice, I'll change this to 3. Or you could have it as 3, it doesn't matter. But sometimes if I'm nice, I might ask you, hey, what's your explanatory variable and what's your response variable? Identify the response, which is your y, and explanatory variable, which is your x. That's to guide you in the right direction, right? It also kind of touches on chapter 1 stuff that we've already learned. And so it's a nice way to tie it all together. But why do you need to figure out which is your y and which is your x? Well, because I'll give you information on the means and the standard deviations. And so you need to link it to the right variable. Then I might ask you to calculate the slope. Okay. Now, if you think about this sy over sx, right? You want to be really careful that you're using the standard deviation of the y's in the numerator and the standard deviation of the x's in your denominator, because if you think about 2 divided by 1 is very different from 1 divided by 2, right? And so it's going to make a mess if you mix those up. But because everything hinges on your slope that you calculate, I will follow through and make sure that it's part of why it takes a while, because if you don't get the right slope, but you follow through and you do it correctly with that slope that you found, then you did it. Okay? Or on the flip side, if you just are blanking, you can't remember how to find the slope, then just tell me, I am going to say the slope is 2 or something, -2 or whatever, something reasonable. But I'll get you to calculate the slope. And then what? You have to interpret the slope. Interpret the slope. This is all review. We did this last day, right? But it's been almost a week, I would say so. And a week it's been. Wow. How do we interpret the slope? We take the general interpretation of the slope and we apply it to this problem that we have. And so what's the general interpretation of the slope for each unit increase in x? We expect a slope increase in the predicted value of y. But you have to apply it to the specific variables, right? So what does a unit increase in x mean, right? And what is the slope? Tell me what the slope is, and then what's the predicted value of y in this case? Okay. I think we had a high school graduates and poverty rates example. It's getting old, but for each unit increase, so for each additional percentage in high school graduate rates, right, we expect a slope increase, which I think was -0.62 or something. So a negative increase is a decrease, but you don't have to get very fancy with it. You can just say a negative increase. That's technically correct in the predicted value of the percentage in poverty. So you have to interpret the slope. This general interpretation will get you part marks, right? Not full marks, because you should apply it to the question, right? But just remembering the general interpretation, and what I'm really looking for is this unit increase statement. Then, once you have the slope and you've interpreted the slope, then I ask you to calculate the y-intercept. Calculate the y-intercept. How do you do that? On your formula sheet, right, I tell you that, and y-intercept b naught, right, so I tell you that b naught is the y-intercept. And it's going to be y bar minus b1 times x bar. Just follow through with whatever slope you have. Right? So many parts. You can do it. Interpret the intercept. Is it meaningful? Which is kind of where we left off last day. Right? What is the intercept? Well, the intercept, if you think about your regression line, b naught plus b1x, you can use the line to remember the interpretation of the slope as well, right? As x goes from 1 to 2, right? You're multiplying b1 by 1 unit, then the only thing that's changing is the y hat is going to increase by a slope amount, right? So you can use this equation, which is on your formula sheet, to remember these interpretations. So what's the intercept? Well, the intercept is the predicted value of y when x is 0. Right? So it's where it crosses the y-axis. I'll bump this down a little bit.
Is that equation just y equals mx plus b?
Yeah.
Okay.
But it would be y equals b plus mx. But yeah, mx plus b. Totally. So interpreting the intercept, right? I want to see something about x being 0, right? And so the intercept is the predicted value of y when x is 0. And then the is it meaningful? Well, your argument has to be, can x be 0, right? Argue whether x can be 0. I'll cut this, try to remember. So it doesn't really matter to me whether you think x can be 0, right? Can the percentage of high school graduates be 0? In my mind, not reasonably, right? We would probably stop measuring high school graduate rates if we didn't have high schools anymore, for example, right? And so, right, but as long as your argument is centered on whether x can reasonably be 0 or not, that's the goal. And then notice how this is all review, because usually I only have 1 day to do regression, and so I cram everything in there that's on the final exam, and now we're just gonna kind of smooth it out a little bit. So we'll work through it again. Okay, so what's the next part? Oh yeah, construct the least squares regression line. That sounds hard. But all I want you to do there is plug in B0 and B1. Remember, the goal is to have a general line, a line of best fit, where I can plug in any value of x, and so x is just going to stay x and predict the value of y. Right? That's our overall goal. And once you have your regression line, okay, whatever you tell me it is here, right? As long as you use that in the following parts, I'm happy. Okay. And so look at all these parts we could have just done after last week. Wow. My husband always gets so peeved because he's like, how many questions is the final exam? I'm like, oh, it's just 10. So, how many parts? I'm like, well, you'll see. There's a lot. But they're just itty bitty. Doesn't matter. I also find it really funny when students ask me, well, how many marks is it out of? Does it matter? I can tell you 10,000. I could just mark on a different scale. It's out of 10,000 marks. Oh my gosh. I wouldn't give you part marks in that case. They'd be full. Probably a 5-mark scale. Something crazy. Okay. Surely we must be done with this question already. Well, but wait, there's more. Then once you have your regression line, you can use it, right? Remember, what was the overall goal? It was to be able to predict values of y, right? And so then I would, given a value of x, oops, predict y. As an example here, just because we did one already last day, but I want you to see it. If we have something like 3 plus 2x, right? I found a slope of 2, a positive 2, which means I have a positive relationship. I have a y-intercept of 3. And so if I have some value of x, right? Let's say let x be, I don't know, 2, predict y. You would find y hat is 3 plus 2 times 2. 2 times 2 is 4 plus 3 makes 7. So my predicted value of y is 7. Usually I make you do another prediction, a second prediction, okay? But with a follow-up. So this is kind of new territory here. New today. So given a value of x, predict y. That's the same as before, right? But with a follow-up, do you trust this prediction? What this is getting at is if the value of X that I've given you is in the range of the data, and by range, I technically mean the domain if you've taken a lot of math, but so in the values of the X's of your data, right, then you can trust that prediction, right? It's a reliable prediction. Whereas if you are using a value of X that's outside the range of the data, right, you have an unreliable prediction. And so often, let's grab this just to talk about. The intercept is not in the range of the data. Okay. And so here, this is the range of our data, right? The values of X that we've built our line on. Now lines continue forever and ever and ever. And so they're not just restricted to this space, but this is where we have reliable estimates, or I should say predictions for consistency. Anything out here, right? Kind of this range of X, we have what's called extrapolation, which is a term that people use kind of in regular speech as well. But extrapolation means that you're using the line to predict for a value of X that's not in the range of your data. And so extrapolation yields unreliable predictions. It is our best guess, and that's kind of the problem. But we do have to be aware that if we're extrapolating, then it's less trustworthy. It's a less trustworthy prediction or a less reliable prediction. Okay. So usually I give you a value of X that's outside the range of the data, right? And then you can still use it to predict the value of Y, but do you trust this prediction? Probably not, right? You would say, no, I don't trust this prediction because I'm extrapolating, right? Or because it's a stressful time, usually a lot of people say, no, I don't trust this prediction because that word that I can't remember. And then they kind of explain, right? Using a value of X outside the range of the data. That's okay too. You don't have to say extrapolation. But if you say it, automatic full marks.
So we'd be given a graph.
Yeah.
Okay.
Yeah, way back here. I would give you the scatter plot, and it's all linked, so. Okay. Then for the last part, do I do it now? Or should we talk about it first? No, I'll do it here, and then we'll talk about it later. What percentage of variability in Y is explained by the least squares regression line on X? Now, of course, those would involve the variable names, right? And so what percentage of variability in the percentage in poverty is explained by the least squares regression line on the percentage of high school graduates, right? That sounds terrible, sounds like a lot of work. But as long as you kind of see percentage of variability or fraction of variability or proportion of variability, right? Something of variability, what you're going to think, we haven't seen this yet, But this tells you it's going to be r squared, which was one of the ways that I could give you the correlation, right? And so now we've seen this r squared twice and we haven't really talked about what it is, but I will tell you this much. R squared is the correlation squared. So then, how could I get the correlation if I give you the r squared, right? If I tell you 70% of the variability in y is explained by the least squares regression line on x, well, then you could take the square root. Right? Take the square root of your r squared, and I'll introduce it here, but we're going to talk more about it. And so if you have the square root, but remember, you get a plus minus out of that, which is the plus minus of the correlation. And then we pick the appropriate sign from the scatter plot. But in this scenario where this question comes last, right, what percentage of variability in y is explained by the least squares regression line on x, then you have the correlation. And I need you to calculate r squared. You just need to square it, and then you're done. Right? So it looks like a big question, but it's actually not. On the flip side, right, this question would have to be a lot earlier if I use it to, right, give you the r squared, right, and then you have to calculate the correlation. But then it would say, 70% of the variability in y is explained by the least squares regression line on x. What is the correlation, or find the correlation, right? And so it would nudge you in that direction. And I would need to do it before you can calculate the slope, right? So probably sneak it in here somewhere. I've got practice questions with both scenarios, so which I have not posted yet, but I will. I meant to, I just forgot. Okay, so there. It's your final exam regression question. I know we need to fill in some cracks here, but we will. I will also put a bonus question on there for regression, but stay tuned. So picking up from last day, right, the intercept, part of the question was interpret the intercept isn't meaningful, right? And our argument had to center around, well, can x be 0? Yes or no? And one of my go-to moves here is to look at the data and say, well, I mean, I don't have any x's that are 0, which tells me that the intercept is not that meaningful, right? It's just where the line happens to cross the y-axis. It doesn't tell me much, right? And so then I can use the scatter plot to determine if the y-intercept is meaningful or not, right? Whereas if 0 is in the range of your data, right? Sometimes if you have things like temperatures, right? Temperatures can go from negative to positive and easily can be 0, and that is meaningful then. But a lot of these scenarios, right, the intercept is an extrapolation. So let's see here. This, the y-intercept is an extrapolation. In this case. I don't know why I wrote it so weird. Oh well. So if we have this regression line that we built, right? Here we're using the variable names, right? The percentage in poverty, but you could call that your y hat, right? Because this is your y-axis and this is your x-axis. And the percentage of high school grads, that's your x. Should we do the interpretation again? I want a different example, but I might not have it. So the interpretation of the slope and the intercept, we already talked about it, right? But the intercept is when x is 0, right? Y is expected to equal the intercept, right? That's our best guess. And for each unit increase in x, it should say increase here, y is expected to increase or decrease on average by the slope, right? But I would prefer it if you just used my canned interpretations. Hers are too wishy-washy. So our goal is to make a prediction, right? Predict the value of y given some value of x. Now, right, if I put in x equals, let's say 82, right, 1, 2, 3, 4, 5, I don't know, 2.5, no. Right, if x is 82, then my y hat, which is the equation of this line, right, is going to be, let's use this line that we were given, 64.68 minus, oops, minus 0.62 times x. Oops. So my y hat is 64.68 minus 0.62 times 82. Making sure you match the scale, right? 82%. We usually convert percentages to decimals, but in this case, they are in percentages, and so you just want to match the scale. So I get 0.62 times 82. Where's my trusty calculator? 0.62 times 82. I get 50.84, 64.68 minus that. I get a y hat of 13.84. And that's what maps back here to our y scale, right? 13.84 looks reasonable, right? This is my predicted value of y if I let x be 82, for example, right? And so if we had a value at x equals 82, it doesn't look like we do, or at this line, we could find the residual, right? But that's from last day, and I don't tend to put the residuals on the final exam, so, but you can review it, right? It's the distance between the observed value of y and the predicted value of y. Applying a model to estimate values outside the realm of the original data is called extrapolation. And sometimes, like we said or saw, the intercept might be an extrapolation. That's okay. It has to cross the y-axis at some point. Here are some examples, and I see examples, kind of crazy examples of extrapolation all the time in the news and on the radio, and all these kind of outlandish claims usually involve some sort of extrapolation. And now the problem with extrapolation is sometimes we have this intuitive knowledge about the behavior, right? And so sometimes we have, you know, if we're looking at a growth chart for children, they grow and they grow and they grow at a pretty linear rate, right? And so children between the ages of, let's say, 1 and, I don't know, when do you stop growing? 12? I don't know, I'm just making it up.
I think for females, it's usually about like, is it like 16, 17-ish? And then for males, it's maybe a little later.
Sounds reasonable.
I think it's because
Say 16-ish.
like, not start earlier. Anyway.
I don't know. I should have researched it before I use it all the time, and I'm always like, when do you stop growing? I don't know. But we grow at a relatively linear rate, right? And so we understand that, okay, this line, I can get fairly reliable predictions. But if you tried to use this line on me at nearly 39 years old, I'd be a giant. So that's bad, right? But that's because, so you would say, well, you wouldn't do that because we stopped growing, right? But what are you actually applying? You're applying this knowledge that, okay, at some point you stop growing. Now, a lot of data, we don't have that knowledge, right? Where we say, well, obviously we wouldn't use that line because it doesn't apply anymore, right? And so that's why we need to be really aware of extrapolation, because sometimes something like this might be happening, right? And you only have a line that's built off of this data and it's giving you reliable estimates and things like that. But if you try to use it beyond the range of the data, right, or beyond the age range where it applies, right, then you're going to get terrible predictions. Okay? I think I'm 39, or maybe I'm turning 39, I think. I'll delete that. There was a while when I was turning 30. So once I turned 28, I was like, I just told people I was 30. And because just rounding up is just easier. Yeah, it was just easier. And so I was, oh yeah, 30. But then I turned 30 and then I just stayed 30 for another 2 years. So for about 4 years, I told people I was 30. It was like close enough. Yeah.
Because people are never going to guess me.
Yeah.
Like I've had people think that I was like mid-20s.
I'm like, that's crazy.
I mean, like when I was 19, someone guessed it was 22. So I'm 20 right now.
I do find that you're only able to tell how old people are that are very close to you in age. Like I have no clue, which tells me you're not very old. Because if you were my age, I'd have a pretty good idea. But yeah, it's just kind of funny when you, yeah. Anyways, extrapolation.
Like I would have not guessed that you were 39.
In a good way or a bad way?
In a good way. In a good way, you seem so much younger.
Aw,
Like I thought
thanks.
you were like late 20s, early 30s.
Whoa!
Yeah, I didn't think you were.
You flatter!
I did not think that at all.
Keep going.
Yeah, I'm like, yeah, totally.
How old do you think I am?
21. But like I said, I'm really bad.
I'm 18.
Wow. I hope that wasn't offensive. Means you can get into places, right? Or
That's fine. There's no-
I think those days have passed. I think you need real IDs now, or don't tell me. Doesn't matter. I would go into a club and then I would leave and hand my ID to my sister, who's like 2 people behind me, and she would get in on my ID. Anyways, bad. It's in the recording too. Yikes.
Oh my god.
Flashbacks, they're gonna come after me. Well, they're closed. All right, so here we have this very weird data set on men's age at first marriage, and the year, obviously. Kind of old data here, but what was happening, right? Early on, right, 1900s, I would say these men were quite old, right, kind of relatively, and then kind of get to some wartime here. People are getting married, but this blue relationship here, it's hard to see that it's blue, but this relationship here looks like a very strong negative linear relationship, right? If I had to describe it, touching on all three things, right? But then something happened, right? Well, I wonder what. Gonna go with World War II-ish, right? And then there was this drastic dip, and all of a sudden we have what I would describe as a non-linear relationship, right? But if you were to use this line, right, to predict values, sure, you would do a decent job over here, right? But a really bad job of predicting the men's age at first marriage, because that's something we care about, I guess. Right, we do a really bad job if we use this line for these years, right? And that's not that far out, right? This relationship changed kind of abruptly here, right? And so that's what we need to be aware of when we're interpreting our line, right? And using it to predict future values. And then even worse, if we use this same line, right? Let's say in the year 2000, I think these men would be about 2 years old, right? That's terrible. But also that's not what happened, right? Started to climb. Now we have a completely opposite, but still linear relationship here, or relatively linear, right? Strong, positive linear relationship, right? And so depending on the range of the x's that we're talking about, you would have different relationships. It's from the BBC. Like I said, now that you're aware and maybe paying attention to it more, you're gonna hear examples of, and see and read examples of extrapolation all the time. And so women may outsprint men by 2156. Wow, that is a headline for sure. What did they use it off of? Well, they used it off of this relationship. Now I have to assume gender norms here. Yes, the men are the blue points and women are the red points. Wow. But also because traditionally we know that men are slightly faster than women, and so winning times would be faster, right? They'd be lower. Now race times are kind of tricky to think about, right? Because usually high is good, right? A high grade is good, a high whatever is good, a high anything is usually good. But in terms of race times, a smaller race time is good, right? That's tricky to think about. But so here we've got data up until it looks like maybe, does it say? It doesn't say what they have used, but maybe up to 2012, right? They've got data up to 2012, and we have this nice, strong, negative linear relationship, right? And both of them are fitting really well. Now here's an R squared. I use a capital R squared, but like I said, lowercase r and capital R's can be used interchangeably. And so If you want to just use a lowercase r squared, that's fine. But the r squared is usually reported on a regression equation. And we'll hold off on saying any more for a bit. Fine. It tells us how well, or it's one measure of how well our line fits our data, right? And so the closer to 1 it is, right? Because if the correlation, fine, let's just do this right here, right now. The correlation goes between -1 and 1, right? Centered on 0. Now, if you square that, if you square a negative value, then it turns values positive, and your r squared is going to be between 0 and 1, which is a proportion which you can convert to a percentage, right? And so here, right, and we said r squared is the percentage of variability in the winning times that's explained by the least squares regression line on the year, right? If we applied to the r squared definition. So the takeaway message here is a high r squared, or r squared, I use a capital R usually, means our line fits well. Fits well. We call it a goodness of fit measure. We've seen the chi-squared goodness of fit test, right? But it's a goodness of fit measure. So,
sorry, does that mean like the line fits our data well, or?
Yeah, so it's capturing a lot of the activity, right? And so notice if we can, I'm going to zoom in here. So here, 0.882, right, is relatively close to 1. And we see that all these dots are pretty tight around the line. Whereas this one is slightly higher. And we see that there's a little bit more wiggle room around the line. And so that's what it's telling us. Nice. So we've got these, but 0.789 is still really high. Okay. I would say even 0.4 is fine. Okay. But right, these are both very high. And if you were publishing a research paper, you'd be really pleased with these r squareds. Right? These are good r squareds. They're something to be proud of. Right? You found a line and it fits your data so well. And then we get into trouble, because then the lines continue forever and ever and ever, right? In both directions. So eventually, at some point here, they cross. And that's what they're saying. Okay, well, this would mean that the women's race times are going to start being less than the men's race times. But another kind of fun thing that we could do that we're not going to do, it's beyond the scope of this course, is you could build a confidence interval around the predictions. We call it a prediction interval in that case, but you have the idea of the confidence interval, and it's basically the same. We just build it around our predictions instead. Here's our r squared. Our r squared. I like to just cram the definition down your throat, because then if you recognize some of those keywords, then you can just stop reading, right? It's a lot of words, but if you see something about kind of proportion of variability or percentage of variability, then you can say, oh, it's r squared, right? Either I give you the r squared or you have to calculate it, right? Those are the only two options on the final exam. But it is the percentage of variability in y explained by the least squares regression line on X. But like I said, as soon as you see something about percentage of variability, you're going to think R squared. And then you can just kind of stop reading. You can confirm, but as soon as you have that trigger, then you can say, oh, I need to calculate the R squared, or I'm giving you the R squared. And so we had a correlation. That's wrong. That's the slope. Let me grab the correlation. I think it's from last day. We had a correlation of negative 0.75 for this relationship. And so if we fit a line, right, there's going to be kind of a lot of movement around that line. The correlation was still quite strong, right? And so negative 0.75. And so we had, this is an error, negative 0.75. So if we square that, negative 0.75, and you want to make sure how your calculator works, because if you put the negative on the outside, right, you might get a negative number. Now, squaring a negative has to be positive. And so this 0.75 squared is 0.5625. So if you get a negative, just be careful. Maybe use brackets around the negative 0.75 to ensure that you get a positive number. So what happened to the rest of it? Well, there are other things that we haven't accounted for, right? Maybe things like the age of the athlete, for example, would impact their running speed. It's an age-heavy day, right? Maybe their height could impact their speed, right? So there's a lot of things that, besides the year, that could impact the running speeds, right? And so that's where the remainder of that variability comes from. Now, we've been working with the high school graduate rate and the poverty rate. And so what we would say is, for our model, we would say 56.25% of the variability in percentage in poverty is explained by the least squares regression line on the percentage of high school graduates. That's how I would give you the R squared. And so here, given R squared is 0.5625. Or I could ask you, what percentage of variability in the percentage in poverty is explained by the least squares regression line in percentage of high school graduates? Then you'd have to calculate the R squared. But here's an example of, okay, if I give you the percentage of variability, then we could say find the correlation. That's that third way that I could give you the correlation. Well, R is the square root of R squared, which is the square root, or plus minus, I should say, because we lose that plus minus when we square it. 0.5625, 0.75, but from the scatter plot, it's negative. since it is a negative relationship. It's okay. See you. So that's the third and final way that I could give you the correlation. We already interpreted the R squared. And it's got the typo. I'm just gonna skip to the. If the R squared is 0.38, then 38% of the variability in the percentage of residents living in poverty among the 51 states is explained by the model, but I'll just stick to that same sentence structure that I've been using. Right, this one on X is missing, but okay. Decision. Let's talk about it briefly. It's not on the final exam. I know. It is possible to have X can be categorical. So for example, if we have an east and a west region, then what could we do? We could say, well, if there's only two possible outcomes, right, then I could say, well, if west is on, right, and it is going to be an on-off switch, right? If west is on, then it's in the western region, right? If west is off, then by default, it would be in the eastern region. Okay? We call that a dummy variable. Okay? And so west is a dummy variable. So it's a 0, 1. 0 if it's off, and 1 if it's on. If it's off, right? So if west is 0, right? Then this is going to be 0.38 times 0, right? Which means my predicted poverty is 11.17. Which region would that be for? Well, it's not for the west, so it must be for the east. We call that the reference level. And so the reference level is kind of when all the switches are off. And we can have more than one switch. So the intercept is the estimated average poverty percentage in the eastern states, because the western is off. It makes your interpretation, or sorry, not your but your calculations really kind of easier, right? Because your X is either a 0 or a 1. Right? And so the slope is going to be now, as we go from a 0 to a 1, we're moving from an eastern state to a western state. Okay? And so then the slope is the estimated average poverty percentage in western states is 0.38% higher than eastern states. And so if you estimate the average poverty percentage in the western state, right, that's going to be 11.17 plus 0.38 times 1. Right? So the math is a little bit easier, but the dummy variable takes some getting used to. It's possible to have more than two categories. Okay. So then this is still a categorical variable. With more than two categories, right? In fact, we have three categories. We've got the Northeast, the Midwest, the West, and the South. Now, if it's in the Midwest would be on, right? I would multiply this estimate by 1. But if it's in the Midwest, it can't be in the West and it can't be in the South, right? And so then these two would be turned to 0. Okay. This is our first glimpse at a sort of a multiple linear regression. Okay. And so how we would write this here, we take this information and we would say y hat is 9.50, right? Take this little guy. And then we would have, I'm not going to write the region 4, I'll just use the Midwest. Yeah. Plus 0.03 Midwest. Plus 1.79 West. Plus 4.16 South. What's the reference level? Well, the reference level is if the Midwest is off, the West is off, and the South is off, leaving just the Northeast, right? And so the Northeast is in the intercept, making it the reference level. Now, what gets tricky is if I turn on the South, for example, right, then the Midwest is off and the West is off. So these are being multiplied by 0 and nothing's happening here. But if the region is in the South, right, then what we say is the Northeast is off, but you're just going to start from the Northeast and then the South adds 4.16 to the intercept. Now, like I said, this isn't on the final exam, but it is on the bonus assignment, and so it might be worthwhile. But each of these estimates, right, has some standard error. Uh-oh, this is sounding like a hypothesis test to me. It is. We can calculate a t. What? I know, right? And we can find the p-value, but usually this is part of output that we would get from Excel or some other software. And so here, this is a p-value. P-value for what? Well, we're gonna focus in on this, but I know, cliffhanger, leave you there for a bit. Which region has the lowest poverty percentage? Now, our y hat is the predicted percentage in poverty, and we start at 9.5. The Midwest adds to the percentage in poverty. The West adds to the percentage in poverty, and the South also adds the most to the percentage in poverty, which means that the Northeast would have the lowest poverty percentage. Outliers. I mention it every year, and I'm sure I've already talked about it, but if you haven't read Outliers by Malcolm Gladwell, I think it's a really fun kind of stats for fun read. And I really like Malcolm Gladwell in general, but Outliers is really good. I think it's 8.3. We're just gonna touch briefly on the outliers. Yeah. And so because what we'll see is if we have a cluster like this, what do you think is happening to the line? It looks to me like the line is being pulled up towards those outliers, right? And if I were to fit this line of best fit by I would probably, if I was ignoring the outliers, I would probably have a relationship like that instead. Yeah. And so depending on what field you're going into, right, you might be dealing with a lot of outliers, especially in a field like biology or all its kind of subgroups. There's a lot of outliers there, right? And so one of the main things that I need you to remember is if you have outliers, it's tempting to delete them, okay? But you want to keep as much data as you possibly can. Okay? So then how do you make a decision, right? You are allowed to delete data, okay? But this data, it happened, right? So do we want to just ignore it? Probably not, right? And I don't know what this is about, but it doesn't matter, right? So we've got this cluster of outliers, not just one, but 4 that happened. So what you're going to do is you're going to fit the line with all your data points. And then you're going to incrementally, I would say, remove one by one, okay? Remove the most extreme, right? And jot down what your slope and your intercept are after each removal. Okay? Once you've reached a point where the slope and the intercept aren't really changing, right? Then that's probably the steady state of the line that you're going to use. Okay, and so there's lots of different ways that we can talk about outliers. But outliers can be a problem in a couple of different ways. Okay? If you have this line or this dot here and this cloud, if you ignore the line tells us, oh, that looks like a relationship for sure. But if you just focus on here, right, I don't really see a huge kind of relationship here. I just see a cluster, right? The line is telling me, oh, that's where it should go. But the line is really only trying to capture this point. And so then we have this illusion of a relationship that's not really there. So there's some terminology, but outliers are points that lie away from a cloud of points. We can have high leverage points. And so if you think about leverage in physics, right, then they kind of pull the line towards them. High leverage points that actually influence the slope of the regression line are called influential points. And so in order to determine if a point is influential, you would visualize the regression line with and without the point, right? Remove the point, or if you have multiple points that you're concerned about, you remove them incrementally. Okay? And does the slope of the line change considerably? Okay? And after that, you're ready to fly on your own and decide whether you want to keep it or not. Often what happens is we end up saying, well, if I keep the outliers, and in this case, we've got the log of the surface temperature and the log of the light intensity of stars in some cluster, and we've got these outliers here. And if we fit the line with outliers, we get kind of terrible predictions all the way around, right? Whereas if we remove the outliers, at least we're able to predict these guys relatively reliably, right? And then the argument would be to model these separately. Right. If you remove them, you're still interested in those guys, but maybe you want to model them separately. And I don't really care about types of outliers. But here, this is an outlier, but it's not changing the slope of your line, right? And so it's high leverage, but it's not influential. Okay. It could, if it just moved up a little bit, it would probably pull that line towards it, right? But because it's in the, basically on the line, it's not going to change the slope. Blah, blah, blah. None of the above. Well, like I said, I'm trying to get to this point, 8.4, which is our last section. I know. And might just be the bonus on the final exam. Wow. Especially knowing there's a twin here. I'm like, have you heard about this research? It's kind of shockingly not that old, but in 1966, Cyril Burt published a paper called The Genetic Determination of Differences in Intelligence, a study of monozygotic twins reared apart. The data consists of IQ scores for what we're going to assume is a random sample, probably not, but of 27 identical twins, one raised by foster parents and the other by the biological parents, hopefully by choice, but that seems weird. Anyways, they were allowed to study it, so who knows?
I saw a test like this done on triplets, but they were divided into families that were the different financial statuses and see how they all turned out.
Crazy.
And two of them actually took their own life because of they all met each other at the end, but they didn't know that they were part of this experiment until like they were a lot older.
Till later.
And then it was just like crazy. But they were all very similar but so different.
Crazy. So here, I mean, yeah, I don't know. They did a lot of weird stuff. And I'm sure we're gonna look back and be like, we did what? But yeah. So we've got the twin raised by the biological parents and their IQ, and then the twin raised by foster parents and their IQ. And we see what, if we had to describe this relationship, I would say we have this strong positive linear relationship, right? And so what's that saying? Well, as the biological IQ increases, well, so does the foster IQ, right? And so right here, we have a strong positive linear relationship. Notice that it gives us the correlation R, right? And so this is a strong positive relationship, and it applies because we have a linear relationship. Output this is our output, but it would look the same in Excel. Okay, so you can use Excel to fit the line of best fit. So you don't have to calculate the slope and the intercept, it'll do it for you. Okay. Now, this is output. Okay. And looks like this, and how you're going to read it is the predicted value of y is the intercept plus the estimate of the coefficient of bio IQ. Okay. And so from here, what you're going to do, we can write in general, y hat is 9.20760 plus 0.90144 times x. Now our y, right? One of the questions, if I give you a scatter plot like this, is to figure out, okay, which is your response variable and which is your explanatory variable. Well, then y is going to be my Foster IQ and x is going to be my biological IQ. My response variable is the Foster IQ and my explanatory variable is the biological IQ. Here for the grand finale? Throwing me off. So, like, wait, what? What was I saying, Neil?
I don't know. Start with the regression question.
Oh yeah, the output. So we can grab the intercept and the slope from this output. That's not what I was saying though. Anyone?
Talking about the outputs.
Talked about the outputs.
Talking about how we do it.
Oh yeah, so thank you. So the Foster IQ is your y. So the predicted value of y is going to be the predicted Foster IQ. Okay? That's the thing that we're interested in predicting. Okay? And your x, your biological IQ, is your explanatory variable. Okay? And so we're going to use the biological IQ to try to predict the Foster IQ. And so what we can do is, well, with the output, right, saves us a lot of calculations, right? We could calculate the intercept and we could calculate the slope, right, using those formulas that we have, right? But now we can interpret the slope, right? If we had to interpret the slope, we would get, okay, what would we say? For each unit increase in x, right, which would translate to for each additional point in IQ for the biological twin, right, we expect to see a 0.90144 increase in the predicted Foster IQ, right, or the predicted IQ of the Foster twin. Things I'm looking for, right? I'm looking for each unit increase in x, right? You want to have that somewhere in there, and talk about what x is. What about the intercept? The intercept, right, is the predicted value of y when x is 0. Right? So if we have to interpret the intercept, I would say, okay, if the biological IQ is 0, doesn't sound very reasonable, right? But if the biological IQ is 0, then I predict the Foster IQ to be 9.2076, right? So is that meaningful, right? That's usually the follow-up, right? Interpret the intercept, and then is it meaningful, right? And so then we would say, well, my go-to move is looking at these values of x here, and because 0 would be way, way, way out here, then I would say, no, that's not very meaningful. But also because we have an idea of IQs, we would say, well, an IQ of 0 probably doesn't exist, right? So then it's not meaningful, right? And so we could use just output like this, and we could still interpret the slope and the intercept, right? One of the things that we want to talk about is whether the slope is significantly different from 0, Okay. And so what does a slope of 0 look like? A slope of 0 looks like this. Well, that should be no change, right? If you think about rise over run, right, then there's 0 rise here, but you could have as much run as you want, and you would have a slope of 0. So a slope of 0 just looks like a horizontal, I have to think about the horizon, a horizontal line like this, okay? Which would mean what about our points? It would mean that our points kind of look like just nothing, just a cloud, right? Nothing's happening here. And so what happens as we develop a relationship like this, right? Our slope becomes significantly different from 0. Uh-oh. That's where that hypothesis testing comes in, doesn't it? Doesn't it? Significantly different from 0. We've done that before, but never for the slope. Okay. Now, you could say, well, my hypotheses have to be about the parameter, right? They have to be about our betas, which we introduced just briefly last day. And it's not on your formula sheet because we're not really going to do it, but for completeness, let's see here. Beta, we only test the slope. So beta 1, and I'm gonna run out of room here, I think. Does it equal 0? My null hypothesis. What's kind of fun and neat is I feel like you might have reached a point where if I give you a null hypothesis, right? Like, okay, is beta 1 equal to 0, or is it significantly different from 0? And then I tell you, well, actually, you just calculate a t, right? Your test statistic is a t, right? And especially if I give it to you like this, then you know how to find p-values associated with t's. And I know what you're thinking, well, what's the degrees of freedom? It doesn't matter because it also gives you the p-value, right? 1.2 times 10 to the negative 9. That's, well, you have to move your decimal negative 9 spaces, right? And so 0.00000, let's say 8 zeros, and then 1, 2, right? Very, very, very small. What does that mean? It means I have a very small p-value here. Okay? It's associated with the slope. Okay? And so, and you can do the same thing with the intercept, but we don't really care about the intercept. We focus on the slope. So if I have a very small p-value, right? 0.0000008 zeros, 1, 2, then I have enough evidence to reject H naught. Well, if I'm rejecting H naught, then that means that my slope is significantly different from 0, right? Which also means that there's kind of something happening here, right? The biological IQ is a good predictor. It is helping us predict the Foster IQ. And I can't remember if there's an example here. Here, I already talked about it all, but I want to show one where there's more than one X, but I don't think I'm going to get it. That's okay. I'll go back up here. We could incorporate more values of X, right? More variables, more explanatory variables, but then we've graduated into multiple linear regression, right? I have multiple X's But you would construct your equation the same way that we did with those categorical predictors, right? Or those categorical explanatory variables, right? You would just snag the coefficient from the output and you can plug in a value of X. But that's, I think, a bonus assignment. And so I'll leave it there. But there's a lot of information here. Let's just focus on the multiple R squared. Right. So there's an adjusted R squared, multiple R squared, should be pretty similar for a simple linear regression. I'll use the multiple R squared. That's going to be our R squared. So if I gave you this output and I asked you what percentage of variability in Foster IQ is explained by the least squares regression line on the biological IQ, you would say, that sounds like R squared, right? You're given the correlation, so you could just square it if you wanted to. In fact, let's try it. 0.882 squared, I get 0.77924. Surprise, surprise. There. And so it's just given us all this work that we already know how to do, right? But it's kind of a shortcut. So then, right, 77.79% of the variability in Y, but Y is the Foster IQ, is explained by the least squares regression line. So this line on X, which in this case is the biological IQ. And there are more slides, but usually I do the end, like the movies, a happy ending. They all lived happily ever after. Anyways, like I said, if anything, it'll be a bonus question. So not to worry. Any questions? I guess I already did my B
You
and
square rooted the multiples R squared.
if you square root it, you should get
The R, okay.
the R. So there's that relationship of R, so the correlation and the correlation squared, or you can move back. But when you go from the R squared, right, then once you take the square root, you have to tack on the negative, but you'll only know if it's negative from the scatter plot, right? And so if it's a negative relationship, then you'll want to tack on the negative onto your correlation.
What's the difference between the word answer if you're giving the correlation, like if you're asked to give the correlation, or if you're asked to give the R squared? The difference between the sentence that you spit out at the end.
Yes. So, do you mean here?
Yes.
Okay. So, I give you a scatter plot. You have to tell me what your X and Y's are, right? Just so you can keep them straight. Might help to jot down what your X bar and your SX are and your Y bar and your SY. And then in here, I would sneak in and I would say 77.79% of the variability in Y is explained by the least squares regression line on X. And then it would say, find the correlation, right? And so then if you're asked to find the correlation, right, then you know that, okay, that's percentage of variability, that's my R squared, I have to take the square root, I have to look at the scatter plot, if it's negative, I have to tack on a negative. Right? Or, right, I give you the correlation, And then at the very end, what percentage of variability in y is explained by the least squares regression line on x? Then you need to calculate r squared. Right, so those are your two options.
It's just the reporting of them part of them.
Oh, you just calculate it here.
So you don't have to report it. You don't have to say, because we have
No.
a sentence of, oh, the percentage of.
No, it'll be in the question. So here the question leverages the fact that you know what the definition of r squared is.
Okay.
Yeah. And when I give you the r squared and I ask you to calculate the correlation, right, it leverages the fact that you know that it's the r squared square rooted plus minus.
So we won't have to say like 56% of the variability and the percentage of poverty is explained by the least squares regression line.
No, it'll be in the question.
Cool, cool, cool.
Yeah. Nice. Any other questions? Then I guess the last question is, do you want to come on Friday? I know, kind of a weird question to ask. I'll let you think about it. No one wants to say no?
What would we do?
What would we do? What I could post the review questions, but then I'd be using up your review questions because I don't have a ton. Or a long weekend might be nice. Fine. With that,
I'm home with the speaker.
I'm, okay. That's cool.
That's cool.
I release you. You are free. You did great. And I forgot to pull it up, but I have a SpongeBob that says I made it through stats and I only cried twice or something like that. So, but I don't have it anywhere.
Thanks for teaching us everything.
Thank you for coming. That's nice. I'll be around before our final exam, but it's not for a long time. So, and I'll send out an outline for the final exam and then we won't have to meet on Friday to do it. How about that? That might be nice. All right. With that, good job. I'm going to end it here. Stop this.